Good afternoon, student. So today we came to our plumbing class day 12. So today we are going to deal with a new topic called garden irrigation system. Okay. Uh, so we'll be solving a problem and we'll be seeing how to how to find the pipe sizes of this garden design. Okay, last day we were dealing with this fountain system, and with regards to that, we have covered the topic. So today we will be dealing with garden irrigation system. Okay, so garden irrigation system in the sense, we have different types of providing water to the for gardening. Okay, that is, we have drip irrigation system, and we have sprinkler system. Okay, we can use a pipe connection also for that. Okay, and normally, uh, potable water will be used. There is abundance. Okay, if there is abundance of potable water, we can utilize that water for you know uh, for gardening purpose. But mostly only 10% of the potable water will be used normally. Okay, for gardening purpose. In some cases, if there is some sewage treatment plant (STP) and all, usually the water which is being produced after the treatment, that water will be utilized for gardening purpose, and as well as for flushing also. So not only that, we can use rainwater also for gardening. Okay, mainly this potable water will not be used. If at all, if they use, only 10% of the potable water will be used. Okay, because that's a drinking water. If there is more abundance of that water, only we will be allowing to supply it to the garden. Okay, or else we will be using any other water source for gardening purpose. Okay, so today we'll be dealing about garden irrigation system. Okay, so without wasting much time, I will share the screen, and each day I will be taking one topics only, so that you can go to the link and you can just focus on one chapter or one topic, and you can study from that. Okay, and let me share my screen. So today I will be studying about garden irrigation system. Garden water irrigation system. So garden water irrigation system. So you know that in irrigation system there are different methods, like you'll be using sprinklers, right? There are different types of sprinklers. Okay, and the sprinklers, depends upon how much length or how much diameter you want to spray. Okay, how much diameter that you want to spray. You will have different types of sprinklers. It will be available. It will be available in the market. Okay, like if you want complete rotation, or if you want to complete diameter, you will be getting that type of pop-up sprinklers. Or if you want to focus only on one arc, or a one portion only, you can adjust, and you can spray, or you can supply water to that particular location. Okay, and you can just adjust so that the diameters also can be varied. How much diameter, or how many rounds, or what is the range of diameter through which you can spray it. Okay, it all deals with that irrigation system only. Okay, you have different, there will be an irrigation system like this. Okay, you can just turn it, and you can just spray it to another a greater area where you may, where you grow some paddy field or something like that. There is a big area. So this sprinkler system mainly will be using in gardens and all those. landscapes, etc. Right? So you have seen all these things, right? Uh, Sprinklers and all those things that usually we use in gardens, right? So now we are going to deal with a small general topic or general thing about the irrigation. Now, first one we are going to deal with the water storage. So, how much water should be stored for irrigation? Okay, so how can we know it? Like, what is the thumb rule for just knowing how much should be the water? Okay, so first one, water storage for irrigation. Like irrigation system could be by hose or automatically using pump, electrical valves, timers, and sprinklers. So usually in irrigation systems, it will be by the hose. The water will be supplied to the hose or automatically using pump. Okay, you will be having a pump. From pump, there will be electrical valves, timers, sprinklers, solenoid valves, etc. like that. So we will be setting timings. Okay, for 10 minutes it will be running, then it will stop. And after 10 minutes, the other sprinkler will start. Okay, then other sprinkler will start. So there will be timing. Okay, depending upon the need or demand, we can have timings, and depending upon the timing, the sprinkler will work. Okay, uh, you know, how much time in a day, like that also we can adjust it. So by using automatically, by using pump, like solenoid valves will be there, and timers and sprinklers will be having irrigation system, or we'll be having drip irrigation also. That is also by the cost of it. We'll be having a by drip will be the water can be supplied to different areas. Okay, like any crops or any vegetable plants like that we can give it. Okay, so as a rule of thumb, the water consumption for irrigation is estimated as follows. So as a rule of thumb, how much water is being consumed, okay, for an irrigation is being estimated as follows. Like it is the green area into 0.02 meter cube per day. So in a day, so if you are this is the formula. Okay, you have to multiply with 0.02 meter cube per day. Uh, for the green area that you are trying to give water, okay, or where you are trying to give water for irrigation. Okay, if the green area is something like, for example, if it is 500 square meter area, so for a 500 square meter area, okay, you are trying to give, you know, method, any irrigation method or any water supply method. So what should be the consumption? How much water it is being consumed? Okay, in a general thumb rule, okay, we can say that just know the area in square meter. Just know the or just find out the area or how much area that you want to give water, and just multiply with 0.02 meter cube per day. You will be getting the uh, you'll be getting the storage, okay, or the consumption, how much water that you have to need to supply. You might be getting it from this formula. Green area into 0.02 meter cube per day. Okay. So for example, suppose we have a 500 square meter green area to be irrigated. Calculate the water storage and the pumping rate per hour. So if you want to irrigate an area of 500 square meter, how much should be the water storage? Okay, how much should be the water storage? Or what should be the tank capacity? Or how much water you have to be storing in a day? Okay, and the pumping rate per hour. How much time you have to fill that water? Okay, so this is as a thumb rule. Just we can implement this. Just multiply the square area in square meter into 0.02. Okay, into 0.02 meter cube, you'll be getting the estimated water consumption per day. Okay, so if this is a question, so what will be the water storage? Multiply 500 with 0.02, you will be getting almost 10 metric cube. You will be getting 10 metric cube. Okay, 500 with 0.02 is 10 metric cube. So the the water storage or the tank or water capacity in a day for a 500 square meter area is 10 meter cube. Okay, so you have to supply that much water, and the pumping rate can be 10 meter cube per hour. Okay, it depends. Okay, if you want to store 10 meter cube in 1 hour, you can use that rate. So normally the pumping rate is 10 meter cube per hour. Okay, 10 meter cube per hour. So, so this is just a an estimation. So if you get a project something like that, ask if you need to know some estimation or how much should be the storage tank, you can use this as a thumb rule and you can find out what will be the water storage, okay, or what will be the storage capacity of water for that particular irrigation or that particular landscape of this much area. Okay. Now, another some of the important thing that if you are trying to design a sprinkler or if you are trying to know the pipe size of, if you are trying to use sprinkler system, you are trying to use sprinkler system in a for an irrigation, you need pipe size, you need how much should be the pressure and all those things. You should be able to know it. So, so regarding this, the requirement of water. Okay, this is some of the general information that you need to know. Okay, the requirement of water for gardening is taken as 10% of the potable water demand. Potable water demand means the drinking water, the pure water that we use for other purposes. Correct. So, so so the requirement of water for gardening. So gardening, that it is not necessary that you need a fresh water or a potable water. That is not always necessary because it is used for gardening, right? We don't use drinking water. Normally, we don't use drinking water for directly for gardening purpose. But if there is no other water and if you have sufficient amount or if you have a large amount of abundance of potable water or a drinking water, then you can use that. Okay, so it is been said that requirement of water for gardening is taken as 10%. It is taken as 10% of potable water demand. Okay, sometimes garden water is separated from potable water due to some reasons that is explained here. So normally when we are trying to design a project, a plumbing project, actually I have already explained this before that we have we sometimes we need to construct two different tanks, two different overhead tanks. One is the domestic tank and another one is the flushing tank. Okay, or one is the potable water tank and another one is the flushing purpose, or for gardening purpose you can use that. Understood? So when you are separating that both, this domestic water tank or potable water tank, that water can be utilized for drinking and washing and bathing, etc. And the other water which is stored in another tank, that can be used for flushing. Flushing in the sense, flushing that water can be directly given to the water closet, as well as you can use it for the gardening purpose. So, in a general term, it has been said that the requirement of water for gardening is taken as the 10% of the potable water demand. So, if you are using potable water for gardening, it is normally taken 10% of it. 10% is the potable water which has been taken for gardening purpose. So the garden water is separated from potable water due to reasons. So sometimes garden water is being separated from potable water that I have explained just now. Why we separate this water. Okay, what is the reason for separating the garden water from this potable water? The reason is availability of non-potable water in abundance. Okay, suitable for gardening. So if there is an availability of non-potable water means it is not okay, we use potable water for drinking purpose and all other purposes. So if there is an availability of non-potable water, in abundance. Okay, we can use that water separately through the overhead tank, a separate overhead tank, and that water can be used for flushing as well as for gardening. Okay, and the second point is requirement of huge quantity of garden water. Because of the huge quantity, because of the requirement, because of the demand of the huge quantity of garden water, this garden water is separated from potable water. Because potable water, we know that it is very scarce. Okay, scarcity of potable water is there, so we cannot use that water in a huge quantity. Correct. So so the requirement of huge quantity of garden water. Okay, so in such cases, garden water is separated from the potable water because of the requirement of huge quantity of garden water. So if the requirement is very huge, we cannot use this potable water at all. Okay. Now the third point is scarcity of potable water to spare for gardening. So you know gardening, right? So you know gardening and how much water that is required for gardening. Okay. Sometimes it's the water requirement is huge. In such cases, what we do is that, like in the scarcity of potable water, we have to use a separate tank for gardening itself. Okay, because there is a scarcity of potable water in that particular location. Okay, and you cannot use that potable water just for gardening purpose because it is very scarce. Okay, scarcity is there because it's very less. So these are the main points where garden water is separated from the potable water. Okay. Now another one important thing that you have to keep it in mind is that when you're trying to you are designing for sprinkler system, you have to maintain these things at the each sprinkler. Okay, like the velocity of the water flow in the sprinkler pipe should be 1 meter per second. So you you have to attain these properties in one sprinkler. In each sprinklers, you have to attain this property. Okay. Then with respect to this only, we will be designing. Okay. So the velocity of water flow in the sprinkler pipe should be 1 meter per second. Okay. So you have to be careful, like when you are trying to design or when you are trying to find out the diameter of the pipe, you have to make sure that the sprinkler pipe is in the velocity of the water flow in the sprinkler pipe should be at the rate of 1 meter per second. Next one, the head at the sprinkler or the pressure required at the sprinkler should be 2 meters. Okay, the head required at the, for example, the sprinkler, which means that there is a lot of sprinklers. The farthest part, the longest part, the end sprinkler, it should need at least 2 meter head. In the farthest point, if there is a sprinkler, that sprinkler should have at least 2 meter head. Okay, so and the discharge from each sprinkler should be 0.3 liter per second. 0.3 liter per second. In 1 second, 0.3 liters. Okay, that is a discharge. So these three things you have to keep in mind. The velocity should be 1 meter per second, head should be 2 meter, and the discharge from each sprinkler should be 0.3 liter per second. So we will be doing a problem right now. Before that, we can just see some more points regarding the landscape in some countries, like automatic, it's been said that automatic landscape irrigation system, relevant course of practice in Qatar. Okay, so it is shown as what is the daily water demand of different trees in that area. Okay, so the peak daily water demand for a palm tree is 120 liters per day per palm. Okay, so you should have that much liters or that much storage, okay, of water. So if you are the irrigation in the sense, you will be having different types of plants, trees, all those things, right? So depending upon that, the water requirement will be different because for each, if you are taking this palm tree with compared with the grass, the water requirement will be different. So if the water requirement is different, the storage of the water tank also should be different, right? Because the requirement of or the demand of water is more, means the more capacity of the water should be there. in the holding tank or in the storage tank. So this is some of the take daily water demand by different trees and shrubs and the grass, etc. Okay, so let's see. For a palm tree, it is 120 liter per day per palm. This is the case of kacha. Okay, so large trees 80 liters per day per tree. It's 80 liters per day per tree. Okay, small trees 60 liters per day per tree. Ground cover 10 liters per day per meter square. So in 1 meter square, 10 liters in a day. Seasonal flowers 10 liters per day per meter square. 10 liters. Hedges 12 liters per day per meter. Large shrubs, okay, 12 liters per day per plant. Small shrubs 8 liters per day per plant. And if it is a grass or a lawn or something like that, it's 12 to 18 liters per day per square meter. So in a square meter, one day at least 18, 12 to 18 in the range of liters should be given. Okay, this is depending upon the learned course of practicing culture. Okay, so some changes will come to different locations. Now, what are the different components of irrigation system? Okay, remote control. There are control valves are there. Okay, there are solenoid valves are there. Okay, so according to the timing, it will open and close. Okay, this is related to the sprinkler system only. So we'll be having a remote control valves will be there, solenoid valves will be there. So depending upon the time, setting some time, 20 minutes, then after 20 minutes or 10 minutes like that, we can set the time. With respect to that, we'll be automated it. With respect to that, it will the remote control valves or solenoid valves will be opening and closing. Okay, and for 10 minutes, two sprinklers will be running. Next for the other 10 minutes, another two sprinklers will be working. Another 10 minutes, another two sprinklers will be working. So we can set it according to the need and demand. Okay? So these are some of the components of system. It is remote control valves are there, and wise trainers will be there. So for some wise trainers, it will be acting as a filter, okay, filtering system. Okay, wise trainers will be there, and where other sediments or other unwanted particles can be stored inside it, and purified water can be sent. Okay, that is wise trainers will be there. Then bubblers or drip emitters. If you are using drip system, we can drip irrigation system. There will be APC bubblers where small droplets of water will be coming. Okay, that is called as drip emitters or PC bubblers. Okay, these all are coming in irrigation only. So irrigation in the sense not only this sprinkler system, we have drip irrigation also. The drip irrigation system are also there. So this will helps to give water in droplets. Okay, and the timing also can be increased. Okay, 1 second how much drops. One we can separate this PC bubblers or drip irrigators. Now we have another one, pop-up sprinklers are there. Pop-up sprinklers. So when it starts to sprinkle only, this will come up. That's why it is called as pop-up. Okay. Otherwise, what happens is that this sprinklers mainly this will be kept in the lawns and grasses. So you just imagine that if the sprinkler, you can see a picture right like this, right? So just imagine if the sprinkler is like this. If someone walks, there's a chance he may hurt his leg because this is, he is standing there. He is standing there. Not only that, when we are using a grass cutting machine and all, we just moving the grass cutting machine, and if it is popped up like this, easily this will be damaged. Okay, by using that grass cutting machine. So when it is in use only, or when the water is being supplied to this only, this will pop up. Okay, this is called as pop up. If there is no water, if the water is not supplied, what happens? It will come down. Okay, it will come down and it will be settled there. So that when you are trying to cut with the gas machine, also it won't damage. So it will come down. So if you are trying to give water, it will go up or it will come down. Okay, so if in the need, only this will work out. Okay, this will come up. Okay, so that is called as spray pop-up sprinklers. So spray pop-up sprinklers, its features, there are the different diameters: 5 inch, 8 inch, 10 inch, 12 inch, 15 inch, like that. There's different, you know, diameters, and you can see that uh, uh, there is a system called as PR system. Okay, there is a system called as PR system, where it's a pressure reducing system, or a pressure reducing in the stem. Okay, stem means that thing only. Okay, where it can restrict the water loss up to 70% if nozzle is removed or damaged. So this is the nozzle. This is the nozzle, the tip of it, and it can restrict the loss up to 70% if nozzle is removed or damaged. Not only that, this PR system, pressure reducing, or pressure regulating, not reducing, pressure regulating only, system or in system. What happens is that you can save lots of water, because in some cases, the sprinkler will be just emitting water. If the velocity is very high, lots of water will be wasted due to evaporation and all those things. We be spraying something like that. Okay, and when we are using a PR system, what happens is that it will precisely maintained, and what happens, the required amount of water only will be flowed. Okay, the required amount of water only will be flowed with precision. Okay, with precision only. Okay, so with precision only. Okay, if you are using a PRS system, also if you are involved in it. Okay, and now another one is rotor pop-up sprinklers. There are different types of sprinklers. Okay, rotor pop-up, it will be like that. Okay, rotor pop-up sprinklers and rain curtain technology. So you can see how it is being sprayed. Okay, it will be going in a very smooth and in a precise manner. Okay, rotor pop-up sprinklers. Okay, and you can see how the installation of pop-up sprinklers. So this is the section view. Just imagine like this. So the pipeline will be coming till this much. The pipeline will be coming till this much, and uh, and from there you can use a flexible connection, and you can keep it like this. So this is the sprinkler. So the sprinkler will be set inside the ground. Okay, it will be set inside the ground, and you can see here it will be grasses, or all those grasses will be filled there. Okay, and when if you need to sprinkle water, what happens? There is a pop-up. It will come up, and then it will start to sprinkle, or then it will start to spray. Okay, at that time only it will start to spray. If it is not in use, what happens is that this will come down. That pop-up will come down, and it will settle there. Okay, and I have said you that why we are doing like that. This it will damage. Obviously, it can get damaged. So this is the installation of pop-up sprinklers. Okay. So now coming to another one, drip irrigation. I will show you the to calculate the dimension. Before that, I will explain what is this drip irrigation. So avoid wastage through overspray and evaporation. Deliver it directly to the plant. So if you are trying to plant something like that, okay, in an irrigation, if see sometimes that if you are doing this sprinkler system, what happens? There is a lot of chance. You can see here. There's a lot of chance of wastage of water due to evaporation and overspray. And you can see always this water will be flowing through the unwanted areas. Okay, without getting much impact in the plants. Okay, so in that cases you can use drip irrigation, where the abundance of water is not there. You can use drip irrigation, where you can save lots of water, because this drip irrigation will be flowing in drop by drop by drop only. So we can use drip irrigation. So this is a drip thing that we have already seen. Okay, from this it's a drip emitter. So from there the water will be coming in droplets. So no water can be wasted like this evaporation and overspray. Okay, this water balancing diagram. There is a one more topic is there. I will explain it in that topic. Okay, water balancing. So how much should be the water, potable water, how much should be the overhead tank water. But it's a water balancing. It's a different topic. I will explain it in the coming classes. So this is the drip system, and that is the sprinkler system. Okay, so we can just see how to find out the sizes. Okay, how to find out the sizes. Okay. So this is the question. So listen carefully. Calculate the size of the garden water pipes for the following network along the storage capacity and height of the overhead tank. So in this question, we have to find out what should be the height of the overhead tank in order to get a sufficient pressure at the end of the sprinkler. Not only that, we have to know what is the storage capacity, how much water has to be stored for this setup, okay, or for this network. Not only that, three things we have to know. One is the overhead tank capacity. Next, what should be the height in which the overhead tank should be placed in order to get a proper pressure. Then third one is the water pipe size. So these are the important things. So if we know these important things, we can do any calculations. Correct. So the main thing will be coming in a garden system is the pipe size, the tank capacity, and the head, how much height it should be, right? So this is the reservoir or the tank. Tank, okay, and the length is given. Okay, the length is given 20 meter, 100 meter, 50 meter, 150 meter, etc. like that. Here also another branch is going, and you can see a point like this. Point like this. Okay, 1, 2, 3, 4 points. So it is said that you already know that the sprinkler flow should be 0.3 liter per second. So you can see here. Already seen that. The velocity of the water flow in a sprinkler should be 1 meter per second. Head should be 2 meter. Discharge from each sprinkler should be 0.3 liter per second. By keeping this in mind only, we are trying to design. Okay. So the minimum pipe diameter for a sprinkler system should be 20 mm. So you already we can already assume that the minimum pipe diameter will be 20. So at the last pipe, the pipe diameter will be 20 mm. Okay, it is a minimum pipe size. Rest of the pipe size we have to find out. Okay, so we know that the length is given. The length of this is 30 meter. The flow should be 0.3 liter per second, 3 sprinklers, and the diameter is 20 mm for this one. Okay, and this both are same. Okay, so its length is given, and here its liter per second is also given. So different nodes are given: A, B, C, D, E. Okay, so this C is this one, this B is this one, this A is this one, this D is this one, and this E is this one. Okay, so and its length is given here, and its liter per second is also given here. So here its liter per second is given here. So here its liter per second is given here. So here it is given as 0.3 liter per second per sprinkler only. So here it is given 1 liter per second. So we can assume that almost 3 sprinklers are there in this row. Okay, 3 sprinklers are there from point E. Okay, because it is given as 1 liter per second from E. So we know that for a single sprinkler it should be 0.3. So if it is 1 here, at least there should be at least there should be 3 sprinklers. Okay, correct. So this is the question. So here the discharge is given as 1 liter per second. Here the discharge is 1 liter per second. So here the discharge also will be 1 liter. Here also will be 1 liter. Okay. So from all the 1 liter per second is being passing. Okay, depending upon the number of sprinklers or taps, we can just imagine it's a tap. Okay, so for one sprinkler it will be 0.3. So from here you can just imagine, or you can assume that there are 3. So how much taps or how much sprinklers will be there? 1. Here 3, here 3, here 3, here 3. So 4 3 are 12. 12 sprinklers will be there. Okay. So through one sprinkler it is 0.3 and the diameter is 20 and the length is 30 meter. Okay, and let's see. Okay, we can do the question. So just leave this a terminal pressure of 7 meter, that will be finding out. Okay, that will be finding out. Just leave it. I have written this initially. Okay, just we can start the question. So this is the question. Okay, so here you can see the length. This is 20, 100, 50, 150. This is 150, 25. So 100 plus 150 is equal to 250. 250 plus 25, 275. So let's see here. 150 plus 50 is 200. 200 plus 100, 300. So this is the largest length. This is the largest length, right? So we have to take the largest length. Okay, we have to take the largest length. Okay, we have to take the largest or the not the largest, longest length. So we are taking the longest length. So this is the longest length comparing with this. So we can just see the head by this. Okay. So let's see. Now we are focusing on this C. Okay. So the hose diameter will be 20 mm. It is even, and the discharge is 0.3 liter per second, and the length of the hose is 30 meter. So you can see here. So all these are same. Okay. This one is same with this. Diameter is 20 mm. Liter per second is 0.3 liter per second. Length is 30. Okay. So you have to write that. Diameter of the hose 20. Discharge is 0.3 liter per second. Length of the hose is 30 meter. So we only got this much information. From this much information, you need to know what is the head at that particular point. Okay. So not to know the head, we already know that minimum 2 meter head should be there at the sprinkler end. Correct? There should be minimum 2 meter head. Okay. There should be at least 2 meter head at the end of the sprinkler. Okay, so we are going to see how much should be the head here at point C in order to get the head 2 meter at the end of this line. So I will explain once more. This means said that 2 meter head should be there at the end or at the end of this sprinkler or at the end of this line. Correct. So we are going to see this much length is 30 meter. This said here 30 meter. All are same. 30 meter. So we are going to see at the end of the 30 meter or at the beginning of the 30 meter what should be the head or how much should be the head in order to get 2 meter head at the sprinkler end. Okay. So we know that here will be 2 meter head. We need 2 meter head at the sprinkler. And now, in order to find how much should be the head at point C, we need to calculate the frictional loss at this length, this 30 meter. We need to know the frictional loss. So, adding this frictional loss plus this 2 meter, we know that the addition, when you get a value, when you add the frictional loss of this 30 meter length plus 2 meter head, that will be the head required at point C. Understood? So, let's see what is the frictional loss in this line, okay, or in this line. So friction loss you can easily get from Hazen-Williamson's table. So you know the diameter is 20 mm, you know the discharge is 0.3 liter per second. So the length of the hose is also 30 meters. So we are going to find what is the frictional loss, okay. So 0.3 liter per second and 20 mm. So you can see here liter per second 0.08, 0.1, 0.2, 0.3. Yeah, 0.34. So you can take 0.34, this one, 20 mm. What is the friction loss? 155.84 per 1000 meter. So the friction loss is 155.84 per 1000 meter is the friction loss. Okay. So the friction loss for 1000 meter is equal to 155.84. You get it from the Hazen-Williamson table, appendix D. Okay, so at this length, at this line, okay, 20 mm, 0.3 meter per second, the friction loss is 155.84. We get from the Hazen-Williamson table. So what is our length actually? What is our length? Actual length, it is 30 meter. This will be same, okay, for this as well as this, for this it will be same, okay, 30 meter. So for 1000 meter, it is 155.84 meter is the friction loss. Then for 30 meter, how much it will be? 155.84 divided by 1000 into 30. So when you are equating it, you will be getting 4.7 meter. Understood? 4.7 meter is the frictional loss. Okay. So 4.7 will be the friction loss here or here. 4.7 will be the frictional loss at this line. 4.7 meter is the friction loss at this line. Plus, you need to know, you have to get a 2 meter head here also at the end. So in this line end, you will be having a sprinkler. That sprinkler is being at least 2 meter head should be there at the sprinkler. So you know that 2 meter is here and a loss of 4.7 is in this line. So the question is, how much should be the pressure or how much should be the head in this point C, in order to attain a frictional loss, or in order to attain a head, or in order to attain a pressure of 2 meter in this end. How much should be the head here at C? How much should be the head at C in order to get 2 meter head at this end? It is very simple. Just add this 2 with this 4.7. Okay, how much it will be? 4.7 plus 2, it is 6.7. So at least 6.7 meter head should be there at point C in order to get 2 meter head at the sprinkler. Understood? Because there is a friction loss of 4.7. I think that is clear. Okay, we need, when we found out the friction loss in this line, this 30 meter length line, we found out that it is 4.7 meter by using Case-Williamson table. And it is said that we need 2 meter head at this end or at this sprinkler. So if you need to get this 2 meter head at this sprinkler, and if there is a 4.7 meter friction loss in this line, how much should be the head in point C in order to get friction loss of 2 meter in this line, or 2 meter head at the end of this line? It will be 2 plus this friction loss 4.7 is 6.7. Correct? So I think you understood that. So 2 plus 4.7 is equal to 6.7. So you can write as approximately 7 meter. 6.7 you can just approximately write as 7 meter. So a terminal pressure at the tap. At the tap here, in the sense, it is said as this point C only. Okay, this tap. Okay, this area. Okay, the terminal pressure that needed in this tap C is 7 meter, approximately 7. Actually, it is 6.7. We can just round it and write 7. Okay, 7 meter is the pressure required at, the terminal pressure required at tap in order to get 2 meter. Okay, in order to get 2 meter. Okay, in order to get 2 meter minimum pressure at the end. So that's what it is written here. A terminal pressure of 7 meter is to be provided in the extreme end of tap. Okay, this will give a minimum pressure of 2 meter at the end of 30 meter long hose. Okay, of diameter 20 mm. So a terminal pressure of 7 meter is to be provided at the end of the extreme end of the tap. This will give a minimum pressure of 2 meter at the end of 30 meter long hose. Okay, so at this tap you need at least 7 meter. Okay, so the head required at this C is 7 meter. Now head required at this B, how much? Not to get 7 meter in this B, sorry, not to get 7 meter head in this C, how much should be the head in this B? We are going to find out. Okay, because there is a frictional loss in between this. So for the pipe BC, extreme point, for the pipe BC, where is BC? This is BC. This line is BC. This B is the extreme point. So in this extreme BC extreme point, what is the flow? 1 liter per second. Correct? Flow is 1 liter per second. You can see here 1 liter per second. This 1 liter per second is reaching here. You can see 1 liter per second. So in BC, the discharge is 1 liter per second. And what is the length? What is the length? Length is how much? Length of BC is how much? 150. From here to here, this 150. So length is given as 150. Discharge is given as 1 liter per second. We are going to find the pipe size. So you know the required terminal pressure at C is 7 meter. Okay, we have already found. In C it is 7 meter. We know the length, it is 150. We know the flow, it is 1 liter per second. So in order to get 7 meter head in this C, we are going to find out the terminal pressure at B. So for pipe BC extreme point, the required terminal pressure at C is 7 meter. Velocity you already know it is 1 meter per second. It is a given value. It is given value in the sense it's a constant value. The velocity should be 1. And discharge is given as 1 liter per second, or we can write as 1 by 1000 meter cube per second also, because 1 meter cube is equal to 1000 liters. So let's see. You already know a formula Q is equal to A into B, B no Q and B no B. Area equal to pi by 4 d square. From there we can find diameter. Okay, Q is equal to 1 by 1000. It is 1 liter per second, right? So 1 by 1000 meter cube per second into pi by 4. 3.14 divided by 4 into d square into b. B is equal to 1 meter per second. So from there you will be getting b as 35.7 mm. So in the market 35 is not available. So the next pipe is 40 mm. So you can adopt 40 mm pipe. So you can adopt 40 mm pipe. So 35.7 mm is the actual calculated value. So the pipe diameter of BC is, the pipe diameter of BC we got is 40 mm. Okay, the pipe diameter of BC we got is 40 mm. Okay, that is one thing. Okay, 40 mm we got. Now we need to know the frictional loss. We need to know the frictional loss in this BC. Then we have to know that what is the terminal pressure at B in order to get a terminal pressure of 7 in this C. Okay. So we already found out the terminal pressure at C is 7. We are going to find what is the terminal pressure at this B in order to get 7 as the terminal pressure at C. So in order to know that, we have to find the friction loss and we have to add it. Okay, we have to add the friction loss. So first we can find the frictional loss. So from appendix D, Hazen-Williamson table, friction loss equal to 40.75 for 1000 meter. Okay, so you know that the diameter is 40 mm. You know meter per second is 1. Okay, so from there let's see what is the value. So you can see it is 0.9, 0.6 is 1 liter per second, and pipe diameter is how much? 40. Actually, Hazen-Williamson table, 1 liter per second is the flow, and 40 mm is the diameter. So from there, you could get 40.75 is the frictional loss. 40.75 is the frictional loss. So 40.75 for 1000 meter. Okay. So for what is the length? What is the length? 150 meter. So for 150 meter, how much will be the friction loss? 40.75 into 150 divided by 1000 is 6.11. So 6.11 is the friction loss. So if the friction loss at pipe BC is 6.11, how much should be the pressure at point B in order to get friction loss, or in order to get head loss? So in order to get head at point C as 7. So if you need to get 7 head at point C, how much should be the head at point B? How much should be the head at point B? The head at point B should be that 7 meter plus this friction loss. Correct? That 7 meter at point C plus this friction loss. Friction loss is 6.11. So add it, it is 13.44. So the terminal pressure at C is 7. The terminal pressure at B is 13.44. The terminal pressure at the end is 2. The terminal pressure at C is 7. The terminal pressure at B is 13.44 something. Correct. Now, for pipe AB, where is this pipe AB? This one. This is AB. And its discharge is 2 liter per second, because here 1 liter per second, here also 1 liter per second. So 1 plus 1, 2 liter per second. And AB length is how much? It is 100 plus 50 it seems. Okay, 150 will be coming. Okay, 80 is 150. Let's see it's 150 or not. Okay, it is 150. Okay, 100 plus 50, 150. So discharge is 2 liter per second or 2 by 1000 meter cube per second. Length is 150, 100 plus 50, 150. Velocity you already know 1 meter per second. We are continuing the same step. Okay, so same formula, Q is equal to area into velocity. Q you already know 2 by 1000. Area you can write pi by 4 d square. Velocity is 1. So from that equating you will be getting 50.5. It's just increasing after 50. Okay, so 50.5 as the diameter. So you can adopt 65 mm as the standard diameter. Okay, you can adopt 65 mm. Okay, so you can give 65 mm. So you got the pipe diameter and you got the liter per second. So with respect to liter per second and the pipe diameter, can you find out the friction loss? Yes. Go to the appendix B of Irrigation table. Q is equal to 2 liter per second and diameter is 65. Let's see. 2 and 65. Yes, you can see here now. Thirteen point eight. 13.82 is the friction loss per 1000 meter. 13.82. So at AB, let's see, 13.82 for 1000 meter. So for 150 meter, how much it will be? 13.82 divided by 1000 into 150. So you'll be getting almost 2.37 meter. So you'll be getting almost 2.37 meter. Okay, 2.37 meter for 150 meter. So the head required at point A will be, okay, so the head required at this point A, in order to get thermal pressure of 13.44 at B, how much it should be? This 13.44 plus the friction loss at AB. Okay, so the friction loss at AB we have already found out, it is 2.37, and the thermal pressure at B will be, already we have found out, it is how much? 13.11, right? It is 13.11, right? 13.44. So you have to write here 13.44, okay? Not 13.11. It is 13.44 because the thermal pressure that will be 13.44, right? No, it is not 13.44. It is 13.11 only, okay? So this is 13.11. So that is 13.11. So 7 plus 6.1. So 13.11 plus 2.73, so 2.37 is 15.48. So 15.48 is the head required at point A. Now for pipe AD, so for pipe AD, what would be the diameter and all those things we are going to find out, okay? Pipe at AD. So before that pipe AD, we have to see RA also, right? We have to see RA also. What is that RA? This one, this one. This is R, this is A. So we have found out DC, we have found out AD. Now we are going to find out RA. So it is 4 liter per second. So here it is 2 liter, here it is 2 liter, it is 4 liter per second. And length is 20 meter. The length is 20 meter, okay? 20 meter length, 4 liter per second is the discharge. So 4 liter per second, RA. So 4 liter per second is the Q, okay? And length is 20 meter, velocity is 1 meter per second. From there you can find the Q is equal to area into velocity. From there you can find out the diameter. Diameter you will be getting approximately. Now we have to find out the friction loss. So friction loss we can get it from the Wilson table. And for 4 liter per second and 4 liter per second and 80 mm. For 4 liter per second and 80 mm. And you can go to Wilson's table. Okay, 4 liter per second. So you can go here 4 liter per second and 80 mm. 80 mm it will be somewhere here and it will be 17.23. 17.23. So 17.23 is the friction loss for 1000 meter. So our length is how much? 20 meter. For 20 meter, what will be the friction loss? Is 0.34. 0.34. So the head required at point R, the point R will be that friction loss plus the same step that we are doing. 0.34 plus the friction or we can add getting 15.48 plus 0.34 is 15.82. So approximately 16 meter is the overhead tank height. So the overhead tank should be 16 meter in height in order to get 2 meter at the end of the 30 meter long sprinkler end. So in order to get 2 meter, minimum 2 meter at the longest part, the end of the sprinkler, if you need to get the pressure 2 meter head, you have to elevate the overhead tank up to a level of 16 meter. Then only you will be getting that. So we have already found out the longest length, right? We have already found out the longest length. So this length also will be accompanied. Or this length will, or this pressure will be compensated because we have already taken the longest length only. So the pressure at this end will be chosen the longest value. If you are, when we took the longest value and we found out that there will be 2 meter head at the end of this sprinkler, we can blindly we can say that there will be 2 meter at this short length. Okay, or just for verification, just we can see this DA pipe DA. In this pipe DA, we already know the terminal pressure at A, correct? So we have to reduce it. So after RA, we got 16 meter. So now pipe AD. So AD, in the pipe AD, the discharge is 2 liter per second and length is 125. Let's see AD. This is AD, 2 liter per second, and this is AD is 125. Okay, this total length is 150 and this is 25. So this will be 125. This length is 125. Okay, not 150, 125. So let's see. AD. This length is 125. How much is the length? You can give that length. At that point A, we have already found out this 15.48. We have already found out it is 15.48. Okay, 15.48. Give that. Adopt the same size of AD because we have already found it is 65. Okay, for 15.48. So for 15.48, we have already found its diameter is 65. So just give that diameter already there. So adopt the same diameter 65. Okay, head we already know. Pipe we can just assume it as 65 because we have already found out. Then go to the Wilson table, the same step. Find out the frictional loss. So frictional loss we already found out, like it is 15.82 for 1000 meter. So for 125 meter length, what will be the frictional loss? 15.82 into 125 divided by 1000. Okay, it is divided by 1000. You will be getting almost 1.98. So a head available at point D will be how much? We already know that 15.48 is the head at point A. So in order to know what is the head, after that you just reduce loss. 15.48 minus this 1.98, you will be getting 13.5. So the 13.5 is the average head at point B. Okay, at point B is 13.5. Okay, this at point B is 13.5. Next, we are going to find out the point at E. If there is a minimum 7 meter head at E, we can easily say that there will be a 2 meter head here. So if it is coming 7 or greater than 7, we can confirm that at the end of this line, it will be 2 meters. It will be 2 meters. So just we are going to see whether this E, the point E will be getting 8 meter or 7 meter or more than 7 meter. This we are going to see. Right, AB and DE. Okay, Q is 1 liter per second is given. Length is 125 given. Velocity 1 meter per second, that is also given. So adopt the same size of for DC 40 mm. Okay, because we have already found out this and we found out that it is 40 mm. So you can choose that. Then goes to the Racing Williamson table and find out the friction loss. We can get that it is 40.75 is the friction loss. Then for 125-meter length, length is 125-meter length, 40.75 divided by 1000 into 125. Okay, this friction loss is 5.09. Now you reduce 13.5 minus 5.09, you'll be getting 8.41. So it is 8.41 is larger than 7. If it is 7 or more than 7, we can just confirm that at the end of the 30-meter long pipe, the sprinkler has a head 2 meter. Minimum we will be getting 2 meter head. So that is fine. Okay, so we have verified and we have found out that the head available at E is 8.41. So it is fine. Okay, now we have so now we need to find out the overhead tank capacity. Found out the available head. Have we can have 2 meter head at the end of the sprinkler. Okay, and we have found out the diameter also of the pipe. And now one more thing we need to know is the storage capacity. We have already found out the head, how much height the overhead tank should be kept. Now we need to know the storage capacity. So storage capacity means we need to know, this is the formula, number of taps or number of sprinklers that you are trying to give into what is the flow from each sprinkler. Okay. The finally that we need to know is storage capacity. The final thing that we need to know is the storage capacity. In the storage capacity, we need to know this is the formula, number of taps into 0.3 liter per second into this is liter per second. So you have to convert it into meter cube or meter. Okay, meter cube. Okay, per hour. So so what you have to do is that number of taps into 0.3 liter per second. 0.3 liter per second means from one sprinkler, you know it is 0.3 liter per second. So from one tap or from one sprinkler, you know it is 0.3 liter per second. So totally uh, how many taps are there? Just let's see how many taps or how many sprinklers are there. Let's see. Okay. So here it will be 3. Okay, here it will be 3, and so here it will be 3 because 0.3. Okay, 0.3 liter per second from one sprinkler. So here it is 1 liter per second. So it will be at least it will be 3 sprinklers will be there in this line in order to get 1 liter per second, because for each sprinkler it will be 0.3 liter per second. So 0.3 into 3 is equal to 0.9, which is coming approximately as 1 liter per second. So here it will be 3 sprinkler. Here also 1 liter per second only. Okay. Here also 1 liter per second. Here also 1 liter per second. So 3 plus 3 plus 3 plus 3. How much? 3 plus 3 6. 6 plus 3 9. 9 plus 3 12. So total 12 sprinklers or taps are there. So from each tap or sprinkler, 0.3 liters per second is coming. So number of taps, how much? 12 into 0.3 liter per second. So convert this liter per second into meter cube per hour. You just multiply 60 into 60 divided by 1000. So you get 12.96 meter cube, which is approximately 13 meter cube. So the overhead tank capacity is 13 meter cube and with a height of 16 meter. So we have found out the tank capacity. We have found out how much should be the height in order to get a minimum 2 meter head at the end tip of the longest length of the pipe. Then we have found out the pipe diameter also. Okay. So this is the way that we will be finding out the pipe diameter as well as uh, storage tank capacity as well as the height. So that's about the sprinkler system. Okay, sprinkler system. So is there any doubt related to the sprinkler system? You can ask. So we were studying about the sprinkler and designing system. And we have seen a thumb rule for finding out the storage capacity. And we have seen the 10% is being taken as the potable water for gardening purpose. Then we have gone through the drip irrigation as well as we have gone through the sprinkler system, and we have found out solved a problem. And by that problem, we have found out the head, we have found out the storage tank capacity, and we have found out the diameter of the pipe. So these are the main things that we need to know about the sprinkler system. So I think that is clear. Okay. Is there anything else that you need to know? Is there any doubt? So tomorrow there won't be class. The next class will be on Friday. Okay. So tomorrow I will be on leave. So yeah. So keep that also in mind. Okay. Keep that information is also in your mind. Tomorrow there won't be class. Tomorrow is Thursday. Next class is on Friday. Okay. So I believe there is no further doubts. There's no nothing is being asked. So thank you. Thank you so much. So see you one day after tomorrow.